Thank you for the presented. I will show now my work that I have done in my PhD until now, which is basically connect, analyze quantum chemistry data that came from digital fusion theory simulations, employing data mining concept and statistical tools to take some acknowledgement from that, especially from the point of view of interest chemical information. I worked with three data sets. The first one is based on cerium and zirconium oxide mixed clusters. This material is employed in catalysis, normally as a support, but in this case we explored the nanoparticles. The second data set is based on platinum and other transition metals nanolloys. It's also employed in catalysis. And the third data set is based on the adsorption and the dehydrogenation of methane on small transition metal clusters. And our motivation is basically develop the overlap between chemistry and computation, and also develop the material science. In the point of view, we would like to take more, identify patterns inside the data that we work with. It's also our initial studies in this area, so it's also important. And also we have developed some tools that can be used to explore this kind of analysis. The data sets, there are some differences. The first one, we have a lot of data. The next one, the second one, we have less data. And the third one, we have more data, but there are more variables in the systems, mainly because we have an adsorption molecule. So the system is quite more complex. Initially, we have molecular information, like the energy of the molecule, the energy of the state, like HOMO. But we also have atomic information which comes from the atoms, which basically is the atomic charge, the effective coordination numbers, the distance of bonds, also if the atoms are exposed to the vacuum or not. And to apply the data mining analysis, we would like to have a attribute value table, which associate for each molecule, for example, molecule 1, property 1, a value, and not a vector like that. So the first task we did is get this atomic information and obtain some kind of molecular information from that. I did it with a package I developed. I call it Quandarium. It's a Python package. It basically, in this step, it helps me to find the calculations, extract information, and perform analysis for all the data recursively. Some geometrical analysis, but I will address more features of the package ahead. So the question is how to get molecular data from this atomic data. And what we did was basically the following. We have information. Here I call it bag because it's a bag of values. For example, a bag with the effective coordination number of the atoms. For instance, a vector here for the first atom, for the second, for the 30, the 40. And we analyze the data based on a class. So the class just selects some of the atoms. For instance, I selecting the platinum atoms here. So the first one and the second. And then I applied some kind of operator over the resulted array. And I take the molecular information of the average coordination number of the platinum atoms. This example is very introductory, just to have an idea of what it can do. but the structure is very flexible. And to have an idea of how deep you can go, you would have, for example, the class of oxygen atoms, and then the class, a deeper class, a class of the oxygen atoms which are also exposed to the vacuum, and a deeper one, the oxygen atoms exposed to the vacuum with a effective coordination number between 1 and 2. And we can take information from very specific features of the molecule. To do it, I employed also my package, which basically I think can take a bag, the informations, and from that take a class, combine a class, take a class in a bag, and take a class from that, and go directly from a bag to a class. So it's very flexible. You can treat all your atomic information with this package completely recursively, no matter if your molecules have a different quantity of atoms or things like that. So with that, we analyze our data, and we have the attribute value table. So we need to analyze it now. We analyze with correlation analysis. The correlation, there are more than one type of correlation analysis. The one which indeed used was the Spearman correlation. However, I will just explain the Pearson correlation, which is the basic one. Then I will address the Spearman. Basically, the correlation is a number between -1 and 1. And it indicates the sign of this number indicate if it is positive, when the x increase, you expect the y also increase. If the correlation is negative, when the x increase, you expect the y decrease. Basically, it's that. And you would ask how much you should expect. And this question is the same of asking how strong is the correlate, which is the magnitude of the value. So if you have a large magnitude correlation, the dots will be something like that. And for smaller correlation, the dots will not be so close to a linear model. The difference between the Pearson and Spearman correlation is basically that here I show a distribution of data, which is the same of this one, but here I add an outlier. Basically, when you analyze the correlation of these two situations, they are very similar in this case, but in this case, the Pearson correlation falls down a lot, 0.9, while the Spearman correlation did not. It maintains very similar, which would be expected. Basically, it's because in the point of view of Spearman correlation, it's not the analysis don't see this kind of the data, but the ranked values. So it makes it robust to outliers. You could ask if you should trust the correlations, and the answer is that it depends on the size of data and its distribution. Here I present 4 examples. I created this data from the same function, but here I present 40 points. In the other cases, I present just 3. In the first one, we can see that the correlation is what we can expect, a positive correlation with a value close to 0.8. And in the other cases, you can see very different correlations. So we can, to verify if our correlations are indeed trustful, we perform the pointer breaks. We perform a bootstrap analysis, which basically will verify for us if we should or not trust in the correlations. And for most of the cases, we can't trust it. To represent the analysis, basically what we done is present a scatter plot matrix. So for each row in the matrix, we present a filter, and y-axis. And for each column of the matrix, we present a part of the data set. In the first case, for example, we present the clusters of iron and palladium. In the second column, the palladium and copper, and so on. In the x-axis, we present the energy. So the molecules more in the left are more stable, and the correlation are presented in colors. We also add a linear model to help us to see if the correlations are positive, negative, and about its magnitude. Basically, I did it with Quandarium also. So the first thing we can see here is that this is one example of the data sets that I work with. We can observe here that some clusters like iron palladium, iron copper, iron ruthenium, iron rhodium have the characteristic of increase the number of platinum atoms in the surface for the most stable molecules. In some other cases like palladium, platinum palladium, and platinum silver, sorry, there is the opposite trend. It basically indicates that for some combinations of platina and transition metal, the platina will prefer to stay in the surface. In the other case, it will prefer to stay in the core. From that, we explain this result based on a model which consider the radius of the transition metal we combine with platina and the surface energy of these atoms. And based on that, we can go very deep inside the data and take a chemical useful information, such as if you combine two atoms and make a metal nanalloys, which one you expect to be in the surface. So I will not present all the data sets. You can see part of the results in the posters. I did three collaborations from each data set I analyzed. So the main conclusions are basically that it's very easy to assess this kind of information with this strategy. You can have quantitative trends, which is very important because sometimes you have two trends that they seems to be have a different trend that seems to be contradictory, but since they are quantitative, you can compare the magnitude of the trends. This kind of strategy to analyze that data is very little explored, so I expect that in the future it will grow. The analysis have some limitations. The larger limitation, the bigger limitation, is the size of the data. How much it would be important to have a considerably large quantity of data to analyze. The analysis have some considerations in related to the applicability. Basically, you can apply to any kind of material. However, by now, it's important to have some programming skills and statistical concepts. The perspective for the next year in my work is basically finish, complete the final, complete the articles that I work with, that I just presented, and then I will publish. I intend to publish an article just based on how to explore data from quantum chemistry data from the point of view of that data mining and correlation analysis presented it in a chemistry magazine, and also released the package that I work with for other persons to employ, and then I will start to work with transition metal clusters from the point of view of energy regression analysis. Then it's completely inside the machine learning and not data mining. So I would like to acknowledge to these institutions, and thank you for the attention.